I'm hitting record. And let's see, we need to share that screen. And here is quarter 3. All right, we started the, oh, I gotta change my tablet. Is it gonna ask for tablet mode? Yes, okay. We started oh. Hang on, I'm gonna turn this sound off on this phone. There. Okay. We started with intermolecular forces. When we're talking about intermolecular forces, we're really talking about attractions between particles. And I found this little card game example. I'm gonna move. I don't know why I even need, you guys don't even need to see that. I guess I just need to. I found this little card sample and we kind of sorted them out. And I felt like this was a pretty good representation. So if you think about intermolecular forces, if we have an ionic compound, which is what this guy is, the ionic compound is that positive and negative attraction. We talked about that yesterday. Otherwise, we're dealing with molecules. We're dealing with covalent compounds. I lied. This is ionic. This is dipole. So let's talk about what has to happen for a dipole to be there. Well, when you're looking at a molecule, if you have a molecule, for instance, a tetrahedral molecule, that is going to be equally pulling on all 4 sides, this is going to be nonpolar. So this is not a dipole. However, if the force is pulling, because remember, what is doing the pulling is the electronegativity. So if the center atom is more electronegative, all of these will be pulled inward, but it'll all be equal. If the outer atoms are more electronegative, then it's all going to come out, but it's still going to pull equally. It'll be like a tug of war where you have the knot in the middle and people are pulling equally on both sides. That's going to be nonpolar. If, for whatever reason, you don't have symmetry, either, oh wait, let's make this a lone pair. Either because here we maybe be pulling this way, but there's nothing acting against it in that direction. In that case, we would have an overall pull. And this is going to pull harder. I'm going to switch colors. This is going to pull harder going this way, which means this would be the positive end, this would be the negative end. That's what a dipole is. And that's what this picture is that I misinterpreted initially. Here's the dipole, the negative end, here's the positive end. And because of that negative and positive attraction, they are still going to be able to interact. What does that do if they can interact? Well, that means it's harder for them to boil. So they're going to stay a liquid longer. It's going to be harder for them to, if they're attracted, you're going to have more, like the meniscus in a graduated cylinder is caused because water molecules creep up the side and pull their friends along with them. If you don't have that attraction, they aren't going to creep up the side. You won't have capillary action is what that's called. You won't have surface tension. A water droplet balls up, makes a little dome. You guys see that? And if you don't have that surface tension, you aren't going to have that dome. It's just going to lie flat. Go upstairs, find some rubbing alcohol, find some, and put a drop of it on your kitchen counter next to a drop of water, and you'll see the difference. Although rubbing alcohol still has, is still a dipole. Now, if that dipole has an OH in it, Here is oxygen's almost always red when they draw it. Hydrogen's usually white. These water molecules all have a hydrogen attached to an oxygen. If you have an OH in the reaction, they are going to create an attraction between each other. So these are dipoles, but they're dipoles on steroids because they have hydrogen bonding. Okay. So the most extreme, these are going to be more extreme. These guys are more extreme than these guys. This would be the very most attractiveness because they're ions. Then you would have this one, then you would have this one. The last one, you still have a dipole, but the dipole is only momentary. All right, you have, if this is a neon molecule, atom, a neon atom has 10 electrons. If you end up momentarily with more electrons on this side, it's going to be slightly negative. The slightly negative side is going to push away the electrons on this atom, and you'll have a few left on this side, making this the slightly negative side. And in the next millisecond, they've gone back to being balanced and you don't have a charge. So these are called London dispersion. And in the test, it just says which one of these has dispersion only forces, a question like that. What are you going to look for if you have a question that says which one is dispersion forces? You are going to look for something that is symmetrical. If you look at this, this is a little flow chart on polarity. Well, let's not, yeah. First of all, how do you know that you have bonds that are polar? Good question. Look what I did. I made a little cheat sheet here so that because I keep forgetting to, or having to find things. All right, here's our electronegativity scale. These guys, if you subtract 3.98 minus 0.79, you have a big difference. The bigger the difference is going to be ionic. If the difference in a bond is between 0.5 and 2.1, it's going to be polar covalent, which means it's a dipole, and it could be have hydrogen bond and it might not. And these guys down here, these bonds would be only have dispersion forces. Now this is for one bond. But if I go back to this question, it says, do you have polar bonds within your molecule? If you look at carbon tetrachloride, this is a polar bond. The difference between carbon and hydrogen, we can actually check this to make sure I'm not just making this up. Carbon and hydrogen is a different, oh, that's not a polar bond. I am making it up. Let's do carbon, all right, we'll do carbon tetrachloride instead. No, back here. Sorry about that. Each one of these, that carbon tetrachloride is 3.16 minus 2.55, which is going to be 0.61 difference. So that falls in this polar covalent area. So this molecule that I just drew, I can't talk, carbon tetrachloride, who's not very symmetrical the way I drew him. Each one of these is a polar bond. So the first question here, are there any polar bonds? The answer is yes, so we come down here. Are the atoms symmetrically distributed? Yes, they're symmetrical. So this is, then you look, are all the outside atoms the same? Yes, they're all chlorines, so that's a non-polar molecule. So he would only exhibit dispersion forces. If we look at, if we do this, hydrogen is less polar than carbon is. So we definitely have, the chlorine or hydrogen's less polar than carbon, or hydrogen has a lower electronegativity than carbon and a way lower electronegativity than chlorine. So we're going to have a pull in these three directions. So our overall pull is going to be like that. So do we have any polar bonds? Yes. Are they symmetrical? No, they're not symmetrical. We have a polar molecule. If you have nonpolar bonds, the molecule is going to be nonpolar. If all the bonds in the molecule are nonpolar, it's just going to be nonpolar. If you had a situation where you had atoms symmetrically distributed, but they're not all out the same on the outside, we'd have a polar molecule. Okay? So hopefully that makes some sense. All right, so questions about London dispersion, dipole-dipole, hydrogen bonding.
Nope.
No, I'm good.
All right. How about polar versus polar molecules? The key here is symmetry. If they're shaped so that the poles are going to be equal on all sides, it's going to be nonpolar. Okay. All right. The next thing we did was empirical and molecular formula, and that's where we have our fun little poem: percent to mass, mass to mole, divide by small, multiply, tell whole. We come down here. I pulled up a couple questions. So the first thing we do, percent to mass. Well, we have 26.56% potassium. I'm going to change it to mass. Chromium is 35.45, and the remainder is oxygen. How do I figure out what oxygen is going to be? Subtract from 100. So 100% minus 35.45 minus 26.56, 37.99. So we've done our first step. Next step, change to moles, grams to moles. So we have to divide by the molar mass. Potassium is 39. Chromium, lost my periodic table, but look what I did this morning. I put a periodic table on here. And I probably won't be able to read it. 51.9, I can tell that's what it is. 51.9, so we'll call it 52. And oxygen we'll call 16. So now we do the math. 26.56 potassium divided by 39 grams of potassium, 0.681 moles. 35.45 divided by 52 is 0.681 moles. Oh, that's good. 37.99 divided by 16 is 2.37 moles. Okay. So next step, divide by the smallest. Which of these three is the smallest? Well, 0.681. So this is going to be 1. This is going to be 1. 2.37 divided by 0.681 is 3.5. What's the last step? Multiply until whole. So this, let's get a different color. We'll do orange. This guy, 3.5. If you were to write that out, instead of a 3.5, write it out 7/2, because 7/2 would be 3.5. If we want to get rid of the denominator so that we have a whole number, we have to multiply all of them by 2. So we get K2 Cr2O7. All right, makes sense? Anybody have a question on how I did that? All right. Next one's the same thing. First we have to do we've 47.0% potassium, so 47 grams of potassium. Carbon's 14.5. Oxygen is 38.5 grams. Divide by, change to moles, so 39, 12, 16, 47 divided by 39 is 1.21. 14.5 divided by 12 is 1.21. 38.5 divided by 16 is 2.5. What's the next step? Divide by small. So we get 1 to 1, and 2.5 divided by, I'm sorry, it was 2.4. Divided by 1.21 would be 2. So this guy is K2C2O4. Okay, but what does that mean? Well, that means the molecule itself has a mass of 166. So we need to see, does this mass add up to 166? If it does, then empirical formula and molecular formula are the same. But if it doesn't, we'll have to figure out how many times bigger the molecule is. So 39 times 2 plus 24 plus 64 adds up to 166. So the molecule has a molar mass of 166. The empirical formula has a molar mass of 166. So therefore, this is not only the empirical, I didn't spell that right, but also molecular. That's supposed to be no. Okay? The next one tells us that the empirical formula is C2OH4. And it tells us that the molar mass is 88 grams. So this is for the molecule. What is the empirical formula mass going to be? 12 times 2 is 24. 24 plus 16 is 40. Plus 4 more is 44. How many times bigger is the molecule than the empirical? Well, it's 2 times bigger, right? So the molecular formula is going to be C4O2H8. Okay? That make sense?
Yeah.
You want me to work another one, or are we good?
I'm good.
Good? All right. Next topic from third quarter, balancing equations. Of course, that was the Super Bowl week of the Super Bowl. Balancing equations and reaction types. We talked about the different reaction types. We know that one product is synthesis. We know that something breaking apart is decomposition. This is single replacement. And we know double replacement because we worked on those. Those are ionic compound or ionic equations. We did that in November when we did the mystery lab and all that. That's double replacement. But there's one more and type, and that is when you have something that has a carbon and a hydrogen and sometimes an oxygen in it. They're called hydrocarbons. When you burn them in the presence of oxygen, they make 2 distinct products: carbon dioxide and water. Okay, so if you see combustion and there's going to be a question in the final where you have to figure out what it tells you it's a combustion reaction, but it doesn't give you the whole equation. This is what your product is going to be. So these are the hardest to balance. So let's balance some combustion, okay? So what are my products going to be? They're going to be carbon dioxide and water. One carbon, one carbon. So far, so good, right? 4 hydrogens, 2 hydrogens. So I'm going to put a 2 out front. 2 times 2 is 4. I have 2 oxygens on this side. On this side, I have 2 oxygens. 2 times 1 is 2 oxygens. So I have 4 oxygens. It looks like 20 plus 20 is 40. So if I have 2 oxygens over here and 4 on the right side, I need to make that 2. And that's balanced. Okay. If you're doing combustion and you have this is ethane. Oh, not. We have 2 carbons. We need a 2 there. We have 6 hydrogens. We need 3 here. We have 2 oxygens on this side. On this side, we have 2 times 2 is 4 oxygens plus 3 oxygens. How am I going to turn that into 7? Well, we could do 3.5, but that you can't have partial numbers in a chemical reaction. You have to have whole numbers. So what we're going to do, this is what happens with combustion a lot of times, is you have, if you look and you get an odd number of oxygens on one side and an even number on the other, you got to go back and double. So now I'm going to double that guy, which means I have to double that guy. 2 times 6 is 12, so I'm going to do 6 times 2 is 12. Now, 4 times 2, I have 8 oxygens, and I have 6 oxygens. That adds up to 14, so that guy would be 7. Okay? Another combustion. We can't let that oxygen get lost because he's a water molecule, or he's a alcohol. 1 carbon, 1 carbon. 3 plus 1 is 4 hydrogens. So I'm going to put a 2 there. 2 times 2 is 4. I have 1 oxygen plus 2 on the left. I have 2 plus 2 on the right. How is this going to become an even number? Well, I have to double it. So I just made that 2 of those methanols. Now I have to make this guy 2, which makes that 4 oxygens. I have 3, 4 times 2 is 8. So this needs to become 4. And that gives me 4 oxygens. And this is a 2 oxygen there. So I know I have 2, I've got to have 8. What do I do to this guy to make him 8? Well, we need 6 here. So we put a 3 there. Okay. So if you have an alcohol, that can get tricky. By the same token, if you have C2H5OH, we need 2 there, and we need 3 there. We have 1 oxygen plus 2 And we have 4 plus 3. Now, do we need to have even numbers on both sides? No, because we have a way of making this side odd because it is odd. So 4 plus 3 is 7. So if I have a 3 there, 3 times 2 is 6 plus 1 is 7. Okay. You could probably Google combustion reactions and find them and practice balancing them if you wanted to. Those are the hardest to balance. The other ones are not nearly as hard. The one that I gave you on your test that people had trouble with, I wish I could remember it, but never fear. I can open up the test. Where is he? Can I write on that? No. All right, so let's copy it. And that didn't work. This guy, because he's kind of tricky. All right, just start with the left. 3 calciums, we have 1 calcium here. We know we're going to need 3. 1 phosphorus, but there's 2 phosphates, so that means we have 2 phosphoruses. Here, I'll make the T chart. Oh, here, C goes in the middle. 3 calciums, 3 calciums. We have 2 phosphoruses. On this side, we have 4. So what do I need to do? I need 4 here. So I'm going to put a 2 out front. That changes this to 6. That changes this to 4. We're not worrying about the oxygens right now. So my phosphoruses are good, but now my calciums are off. So I'm going to come up here. I'm going to erase the 3. I'm going to make him a 6. Okay. Now I'm going to do oxygen last. I'm going to go to silicon. For silicon, I have 1 on the left. And now I have 6 on the right. So I need to put a 6 in there. Last but not least, we'll do the oxygens. That's 4 oxygens times 2 is 8, times 2 is 16. 6 times 2 is 12. On this side, we have 10 oxygens. 6 times 3 is 18. And look at that wonderfulness. Okay. A lot of people went and did put a 3 here, and then they got a 2 over here, but they never quite recovered. So that's that tough one. All right, any questions about balancing equations and combustion?
No.
All right. Stoichiometry. Basically, when we're talking about stoichiometry, we are simply talking about if you start out with this much, how much are you going to need? So let's use, I don't know. Let's use one of those combustion ones we just reacted, just because. Let's do this guy, 2746. C2H6 plus 702, 4 carbon dioxides, 6 waters. Okay. So let's say that's what we're starting with. All stoichiometry means is if you have 2 of these, you're going to make 4 of these. So if I tell you I have 8 moles of C2H6, 2 makes 4, so 8's going to make twice as much. 8 would make 16. There's 2 ways to do it. The way we've learned, the way that you were probably taught in Gen Chem, is to multiply the known amount, which is 2 moles on the bottom, and the unknown amount, which is 4 moles on the top. So you do that and you get 16 moles. The other way you can do it is you can go, well, I'm starting out with 8 moles of this. Normally 2 is going to give me 4. What's 8 going to give me? It's going to give you the same thing. It's just a ratio. This is just rearranged in this format. And that's what I'm using when I look at the bridge. This is the known amount. So our known amount was 8 moles of C2H6. And we were solving for this much moles. And our ratio was 2 to 4. Every 2 moles of ethane made 4 moles of carbon dioxide. So you multiply 8 times 4 divided by 2, and that gives you moles. Okay? That's the basic process with stoichiometry. But what if we throw something else at you? For instance, instead of telling you moles, what if I tell you, I'm going to use the same one. Let's see if I can copy it. Okay. What if this time, instead of telling you I have 8 moles of ethane, I tell you I have 8 grams. So we have to first change to moles. If we look at the mole map shows you that if you have grams and you want to change to moles, you divide by molar mass. So the molar mass of ethane would be 24 and 6, 30. Divide by molar mass. Now we're on the bridge. Now we look at the ratio. The ratio, we're going from 2 to 4. 2 moles of C2H6 to 4 moles of CO2. So now we've changed to moles of carbon dioxide. Now we got to go back to grams. Molar mass of carbon dioxide is 44 grams in 1 mole. Okay, so it's just a regular pattern. What, though, if I tell you that I have 20 grams of this guy and 20 grams of this guy? I have to figure out who's limiting. In other words, I got to figure out which one I'm going to use up. So which is going to make a smaller amount of carbon dioxide? So I start with the ethane, 20 grams. I said the molar mass of that guy was 30 grams in 1 mole. There's 2 moles in the equation for every 4 moles of carbon dioxide, 44 grams in 1 mole. Then I'm going to do the same thing with this. I'm going to start, instead of 20 grams of oxygen, what's the molar mass of oxygen? Here's another place that people miss things, because everybody knows 16 is oxygen, but this is O2, so you got to do 32 grams in 1 mole. The ratio here is 7 to 4, 7 moles of O2 to 4 moles of CO2. We're still doing carbon dioxide though, so it's still 44 grams per mole. Now, if I get my calculator out, 20 divided by 30 times 4 divided by 2 times 44. 20 grams of ethane would make 58.7 grams of CO2. Now, if I have 20 grams of oxygen, I'm going to make only 15.7 grams of CO2. Okay, If I don't have enough oxygen to make more than 15 grams. So I'm going to use up all of the oxygen. Therefore, oxygen is what we call limiting. And to figure out how much ethane would be left over, I would start with 20 grams of oxygen. And I'm going to now solve for ethane. Times 30 grams and 1 mole. So 20 grams of oxygen is 5.35. 20 grams of oxygen would require 5.35 grams of ethane. We started with 20, so 20 minus 5.35, so this is what was used. We would have 14.65 grams left over, if I did the math right. So, stoichiometry questions.
On the tests, how important is like labeling? Like,
It's multiple choice.
oh, okay.
So you don't have to worry about any labels. You don't have to worry about sig figs, except for the question that says how many sig figs is in this one.
Okay.
I can't say I would go through and give you all the molar masses because it's set up so it's an algorithm. So the questions you get, Aiden gets, are going to be different from Hayden's, and they're going to be different from Brooklyn's. So they may even be different chemicals. They may be different equations. So I can't go through and give, like I gave you guys a list of molar masses for your last test. I can't do that for this. You guys will have to calculate your own molar masses. Use Google if you need to, or Siri. All right, what other questions? The last thing we did was molarity in titrations. Molarity is just another piece of this mole map. If you know moles, moles divided by volume is molarity. If you know the volume of a solution, volume times molarity will get you moles. I'm going to write those things out here. Here, we'll change to different colors since it's a new topic. Okay, so if you know volume and you want to find moles, you multiply. If you know moles and you want to find volume, you divide. Okay, so if we have a situation where we have, what did we use? We had sodium hydroxide, and what do we use for our acid? Oh, KHP. This is called a neutralization reaction. Okay, KHP is an acid, but it is in powdered form. So in our titration, we started, KHP was a mass. So we had, say, 20 grams of KHP. We changed that to moles, molar mass of KHP, I should have memorized. Okay, Google, what's the molar mass of KHP?
The molar mass of potassium hydrogen phthalate is 204.22 grams per mole.
So there's your molar mass. So what did we do? Well, if I go back to my bridge, I started here. And I changed. No, I started here. I had grams, I changed to moles. Now I need to change to sodium hydroxide. So I started, with KHP, and what's my ratio here? It's 1:1. And then how do I change that to volume? Okay, so you might have a question asking you to find volume. So here I am at moles. How do I go from moles to volume? What do I do? Divide by the molarity. So let's say the molarity was 0.150. We'll put molarity on the bottom. Grams cancels, moles cancels, moles cancels. You end up with a volume in liters. Okay? What if your starting point instead of KHP? What if we had done this lab, which is what we were supposed to do on Friday before spring break? And let's say we know that the molarity of sodium hydroxide is 0.150 moles. And we're going to use a burette to figure out the volume. And we're going to start with 5 milliliters, which 5 milliliters, 1, 2, 3 would be 0.005 liters of vinegar. And we want to figure out the molarity of the vinegar. Okay? So first we have to titrate. So we put 0.005 liters into the flask. And we've got 0.150 molarity NaOH. And we start adding that up, and we end up adding, so we had 0.005 liters of vinegar. And let's say we added 10 milliliters of sodium hydroxide. So now we know volume of sodium hydroxide. We know molarity. If we know volume, we multiply volume times molarity. Change this to liters, 0.010 liters. The molarity was 0.150, which is actually about what our molarity would have been had we done this lab. So 0.0 times 0.150 gives us 0.0015 moles. What's my ratio? It's 1:1. So 1 mole of NaOH is equal to 1 mole of vinegar. So we knew volume. We're going to solve for molarity of the vinegar. How do I find molarity of vinegar if I know moles? Well, look back at your mole map. If you know moles and you want molarity, you divide by volume. The volume was what I put in the flask, 0.005. And you get a molarity of 0.3. Okay. All you got to do is just use your map to go back and forth. And they don't give you a complicated titration, but they do give you a titration. All right, questions about that? Do you want more examples of that?
Yeah, let's do one more.
Okay. All right, gotta move you guys over here. This is not the one I want. I want this guy. Do I have titration? Yeah, here we go. Why does it have to be so difficult? All right. Okay. So here is an example. We have sodium hydroxide, and it tells us that we had 0.1 molar sodium hydroxide. It gives us the volume we used. We had 125 milliliters of hydrochloric acid in the flask, and it's asking for molarity. So we start with what's known. Well, we know both pieces here. We only know one piece here. So we're going to start with NaOH. We need to find, uh-oh, what did I do? What did I do? Okay. We need to find the number of moles of NaOH. So we're going to take 0.054 liters times 0.1 molarity, which is moles per liters. Liters will cancel, and we're going to have 0.0054 moles of NaOH. What's my ratio of NaOH to hydrochloric acid? It's 1:1. That means that we have 0.0054 moles of hydrochloric acid. Okay. How do I find molarity? Look at your mole map. Molarity is moles divided by liters. So moles divided by liters. How much hydrochloric acid did I start with? 125 milliliters, which would be 0.125 liters. 0.0054 divided by 0.125. Molarity. Assuming I did the math right. I could have done the math wrong. But I'm assuming that you would have told me, if you're working it along with me, that I did it wrong. Okay, the next one. It gives you the information about the hydrochloric acid. It wants the molarity of the sodium hydroxide. So again, it's a 1:1 ratio. We have to find moles of hydrochloric acid. To find moles, we take volume, and I'm going to change it to liters, times molarity, 0.025 times 0.05. It's 1:1, which means it's 0.00125 moles of NaOH. How do I change to molarity? Divide by liters. How many liters did we use? We used 345 milliliters. Divided by 0.345. Okay. That makes sense?
Yep.
All right. I think that is third quarter now. Any last questions for today?
No.
All right. Well, then we will gather again tomorrow at 1 and have quarter 4 party, which you've only watched lectures online. You haven't gotten to ask questions in person, or you haven't had any when we've asked. So tomorrow, here, let's share that again. Tomorrow we will talk about heat and thermochemistry, gases, and triple points. Okay? So let me know if something comes up and you need to change the time. Otherwise, we'll plan on 1. So happy days, kids.
Sounds good. Thank you.
You are welcome. Have a good one.